This topic is called constant velocity problems, and essentially it's just applied straight lines. So we tend to use the letter t rather than lambda, but they both sort of do the same thing. So we're looking at this boat, it's boating along the water, find the initial position. So we can say that x, y, so at t equals 0, that would be the initial position. xy is going to be 3, 1 plus 0 lots of 1, 2. So that just gives you 3, 1. It's a vector, but it also gives you the position. So it starts at 3, 1. Might actually just put that on our diagram there. So 3 and 1. Okay, we can start plugging in the values at 1, 2, 3, and 4. So at t equals 0, we got 3, 1. At t equals 1, you're going to be adding 1, so you're going to get 4, and you're going to be adding 2, so you're going to get 3. So 4, 3. So it's up like that at t equals 1. T equals 2, we'll add another 1, so that's going to give us 5, 5. And you can hopefully see what's happening here. It just sort of goes up and right. It's an equation of a straight line, as we learned a couple of videos back. But it doesn't, you don't draw the line as if it's going back because it only starts at t equals 0. And then it's probably not a bad idea to do that, and also to label it with the equation. So xy is 3, 1 plus t, 1, 2. Okay, find the velocity vector of the boat. That is just the direction vector, so that is 1, 2. Find the speed. So the speed actually is the absolute value of velocity. Now, when we've done kinematics up till now, we've sort of talked about if you're going left, just flick it positive. But when we talk about absolute value of a vector, this is the modulus. So the speed is actually root 5. Okay. Yeah, that's in kilometers per hour. It's probably not a bad idea, since this is an applied problem, to get an approximate for that. So it's about 2.24 kilometers per hour. Okay, if the boat continues in the same direction but wants to increase its speed to 10, how do we do this? What we need to do is we need to be looking at the vector v hat. So that's a unit vector in the same direction as v. So it's 1 over root 5 times 1, 2. And then we need to be scaling that up, so 10 times bigger. So that's going to be 10 over root 5 times 1, 2. So I'm just going to call this the velocity nu is that. And we can say that that is 10 over root 5 and 20 over root 5, if you want. Now, technically, you've got to get the surds off the bottom. So we can times the top and the bottom by root 5. You could get 10 root 5 over 5. And you can get 20 root 5 over 5, and then they simplify down a little bit more. So that's going to be 2 root 5 and 4 root 5. Now, personally, I don't mind too much, so I'm happy with any of the 3 there. Well, you wouldn't stop in the middle, but I'm happy at either of those 2. Okay. So yeah, that's the process. You scale it down to a unit vector. So this has length 1, and then when you scale it back up, this has length 10. Okay, a big rock is located at 2, 1. So let's pop that on our diagram. So we've got this. Sorry, that should have been at 2, 4. So a big rock is located at 2, 4. We'd like to know when we're closest to that rock. Okay, so how close does the boat get to the rock? So basically what you can do is you can actually look at it as a vector. Sort of like you can use the distance formula or the vector formula, whatever. But x is 3 plus t, and y is 1 plus 2t. And then the rock is 2, 4. Okay, so we get all that information, and we can bring it down, and we can think about what the distance might be between the boat and the rock. Okay, so let B be the boat position, So B, I might do that. Yeah, no, B's fine. So B has coordinates 3 plus t and 1 plus 2t. And let R be the rock position. So R has coordinates 2, 4. So if we go BR, basically, well, it's going to be a bit nicer if we go from the rock to the boat, just in terms of negatives. So that is going to be 3 plus t take 2 and 1 plus 2t take 4, just like that. Okay, so that's going to be 1 plus t, and then it's going to be minus 3 plus 2t. So that is RB. And if we want the distance, so distance is mod RB. So the distance there is going to be square root of 1 plus t squared and minus 3 plus 2t squared. Now, there's a couple ways you can go about minimizing this distance. We could use a calculus method or something like that. We could get the derivative and set that equal to 0. But what I'm going to do instead is just graph it on the calculator. Alrighty, so I've graphed that on the calculator there. You just got to use x instead of t. That's the only difference. And we can draw that there. It's the distance. So we can just go g solve min. Now, that's happening at x is 1 and 2.236. So let's just pop that in. Now, how do we interpret both these numbers? So the y-axis here is actually the distance, and this, I guess it's t for time, but it's the t value along the line. So t is 1. The distance is 2.236. Now, where is the boat at this time? We haven't actually answered that question. So if t is 1, I think we actually figured out where the boat was at t equals 1 before by subbing it in, but the boat is at 4, 3. So the boat is at 4, 3. So that's how we answer that last question. How close does the boat get to the rock? It gets 2.236 kilometers away when the boat is at 4.3, because that's the value for t equals 1. And you can actually sort of see that this point here sort of would be the closest point. That's an example of quite a tricky question you can get with these constant velocity problems, but just watch out for those curveball style questions.